Hello and welcome to this MRCPCH revision video. Today I'm going to discuss the pathophysiology of type 1 diabetes. So let's begin by taking a look at the pancreas. Now here we have a diagram representing the microscopic structure of the pancreas. On the outside in orange we can see the acini. These are the cells which produce a digestive enzyme and make up the exocrine pancreas, and these make up by far the majority of the mass of the pancreas, in the tune of between 97 and 99% of the pancreatic mass. The remainder is made up of the endocrine pancreas, which here is in the form of the islets of Langerhans. And the islets have a number of different cell types which are supplied by a rich network of capillaries that allow the drainage of each of the cell's hormone products. So in this diagram on the outside in green we have the alpha cells, and these are responsible for producing and secreting glucagon. In the centre, the blue cells are the beta cells, and these are responsible for the production of insulin, and the brown cells are the delta cells, and these produce somatostatin. In diabetes, what's happening is individuals that are susceptible through a combination of genetics, exposures and other environmental factors produce autoimmunity against their own beta cells. What happens is they produce T and B lymphocytes, which in turn produce autoantibodies, and these form immune complexes that migrate into the islets, resulting in the infiltration of macrophages, which begin to consume and destroy the beta cells. And that looks like this. So here we have the autoimmune complexes entering the islets, and that leads to a progressive destruction of the beta cells. And as this occurs, the amount of insulin secreted by the pancreas falls. So let's take a look at that in a bit more detail. So here we have a graph representing time and the number of beta cells in the pancreas. And in normal individuals, that number remains pretty constant. But in diabetes, when we have the autoimmunity beginning, we then begin to see a fallen number of beta cells. And this continues until we reach a level where we can no longer produce enough insulin to maintain a normal glucose level. So the number of cells falls further, and proportionally we have less insulin, until we come to a point where we have so few beta cells that we can no longer produce enough insulin to maintain our glucose homeostasis. And it's at this point we begin to suffer symptoms such as polyuria, polydipsia, polyphagia, weight loss, etc. So let's take a look at what happens in the kidney. Now, as the level of insulin falls, the amount of glucose in the blood climbs, and this is represented here. Its capillary is rapidly filling up with glucose that has nowhere else to go. Now, glucose is freely filtered in the kidney, and in a moment we'll see this happening. So it's filtered through the glomerulus into the renal tubules. The renal tubules are capable of reabsorbing glucose, but the sheer amount filtered through exceeds the capacity of the kidneys to reabsorb. What happens then is we see urine containing glucose, so that produces the glycosuria, and the presence of glucose increases the osmolarity of the filtrate, leading water to be secreted by osmosis into the tubules, and this results in the symptom of polyuria. As polyuria progresses, this results in a progressive dehydration and contributes to weight loss through the loss of water weight. Also, because glucose is transported with sodium and glucose co-transporters, we lose electrolytes as well in this process. So let's take a look at things from the perspective of a random body cell. So under normal circumstances, there is circulating insulin which binds to insulin receptors on the cell surface, which opens glucose channels, and that allows the cell to absorb glucose, which can then be metabolized to form energy in the form of ATP. In diabetes, there is no circulating insulin, so the glucose channel in the cell membrane remains closed. As a result, the cell cannot absorb the glucose. Now, even though there is enough glucose in the blood, the cell cannot utilise it, so the cell begins to starve as it can no longer absorb glucose and it can no longer produce ATP by normal means. This results in a cascade of hormones designed to kick off the catabolic processes to produce alternative fuel sources. So we're going to look at that in a lot more detail now. So in diabetes, our level of circulating insulin falls, and as insulin falls, its inhibitory effect on glucagon is reduced. Consequently, the activity of glucagon goes up, and the combination of these two factors causes an increase in glycogenolysis. Now, early on we saw our unhappy cell, and our unhappy cell triggers the release of stress hormones, namely adrenaline, growth hormone, and cortisol. Adrenaline further reduces the secretion of insulin, exacerbating the glycogenolysis. Cortisol increases the rate of proteolysis, products of which enter gluconeogenesis. Growth hormone reduces insulin sensitivity and therefore reduces glucose utilization. Adrenaline increases the rate of lipolysis and releases free fatty acids. This results in further reduction in insulin sensitivity and leads on to ketogenesis. And the presence of ketone bodies further reduces glucose utilization. All of this results in an further increase in serum glucose. Now, as we no longer have the action of insulin to counter that, this accelerates the pathology. If no insulin is given, this process will continue on, leading to ongoing production of ketone bodies, which eventually reaches a level that can no longer be excreted by the kidneys. And once this happens, we begin to have ketoacidosis. Ketoacidosis will then lead on to coma and eventual death.